All right, now we're finally at 2023 May paper 2 time zone 2. Okay, so again, this is a calculator paper. So have your TI calculators and formula booklets ready, and let us begin. So number one, we're hit with a linear regression problem. So we're gonna have our list L1, list L2. We're gonna put that into our spreadsheet, and we should automatically be able to calculate our R value as well as our A and B values here. Okay, so H is the dependent variable, D is the independent variable. So if you look here, depending on the number of days where the experiment has been running, we can find H, the average height. So we can imagine that as the days go by, the height of the plant is going to go up. So we just got to put in D as our X variable, our H as our Y variable. Right? So A and B will be taken care of by our calculator. Then once you have that model, we'll find what H will be when D equals 20. Okay, so let's head on over to our calculators to fill up our values. So we have D equals 2, 5, 13, 24. If you go to your spreadsheets, lists and spreadsheets, we can just enter in our numbers. So we would get 2, 5, 13, 24. Then we get 33, 37, 42. Next, moving on to B, right? So our Y, our dependent variable is going to be 10, 16, 30, 59, 76, 79, and then 82. Oops, 82. 76, 79, and then 82. Right, so we have 7 data points. And we're basically going to do statistics, calculations, linear regression. Right, so our X list is going to be our A. And then we're going to have our symbols here. Okay, so we're going to have our A list. And we're going to have our B list. And we're going to have our brackets here. Let's just calculate, let's just add the square brackets to indicate that this is a list. So our X list is going to be the list of values in column A. Our Y list is going to be the list of values in column B, and we get 1.93 for our M, and our B is 7.21 or 22, and then our R value, the Pearson product moment correlation coefficient, that is 0.99. Okay, so first of all, if H equals AD plus B, then A is going to be 1.93, B is going to be 7.22 if you round it. So H is going to be 1.93 times days plus 7.22. Our R value was 0.991. And using this regression line, what's the average height of the plants when the experiment was running for 20 days? We would do 1.93 times 20 plus 7.22. If you put that in your calculator, we should get 45.9 centimeters. Right, so that's it for part 1. You just gotta use your equations, use your calculator, and the calculator will do everything for you. Right, so you just put in your list 1, list 2. Make sure we don't switch that up. X is the independent, Y is the dependent. Then we find M, B, and R. Right? Also make sure we get R, not R squared. So we have a positive correlation, right? R being 0.991, very close to 1, means that it's a very strong positive correlation where D increasing means H is also increasing. D decreasing means H is also decreasing, right? So that's the positive correlation we have. That's it for number 1. Let's move on to 2. 2, we have a triangle problem here, right? So we have point P that's directly between the 2 buildings, right? And the angle of elevation. So if you look up from the ground and you look up to the 2 buildings at A and B, we have our 2 angles of elevation, which is theta. And let's look at what we're being asked. Okay, so we're given a bunch of info like this. We want to find APB, right? So you don't necessarily have to like understand the full picture of what's happening. We just have a diagram. So we have APB. So the measure of that is going to be 180 degrees minus 2 theta. And we might want to find out what theta is. Okay, so let's try to look at the info that we're given. Okay, so actually, in this case, it's better to use triangle APB rather than the thetas here. So I guess we're going to use theta later on in the question. First, we're going to look at triangle APB only. So if you look at triangle APB, we're given 3 side lengths, and we're trying to find any other unknown angles. So this means whether it's SSS or SAS, we're always using the cosine rule or the cosine law. So we have our angle. Let's call this phi, right? So the side that's opposite to phi is 154. So I would set up an equation where we have 154 squared equals the 2 other side lengths, like 150 squared plus 90 squared minus 2 times 150 times 90. Then cosine phi is what we're looking for, right? So you can check back at your formula booklets. This is the isolated side that's opposite to the wanted angle here, right? So if you put this in your calculator, you get 154 squared minus 150 squared minus 90 squared all over negative 2 times 150 times 90. That's going to be cosine phi. So if you do phi equals cosine inverse of 154 squared minus 150 squared minus 90 squared all over negative 300 times 90. Right? I just did 2 times 150 here. So if you put this in your calculator, you should get a reasonable answer. And always check whether it's in degrees or radians. Okay? So the question says, okay, so the question didn't specify like what we want, so you could write it either way. But let's put this and see what we get. So I guess instead of writing negative, we could just write cosine inverse of 300 times 90. And then I'll do 150 squared plus 90 squared minus 154 squared. Okay. So let's put that in our calculators. So you can kind of hit shift cosine, right? Or for me, if you just hover over here, we have cosine inverse. And in goes the numerator and denominator. So for the numerator, we have 150 squared plus 90 squared minus 154 squared. Then I want to close my brackets because I want to do this all together. And then I want to divide by the numerator all at once. And I would just get brackets just in case. I would do 300 times 90, close brackets. Right, so I'm taking the cosine inverse of this whole thing here in order. That should be, if you get decimals, 1.31. Right, so is this degrees or radians? Well, my settings are currently in radians. So I could write this as 1.31 radians. If I wanted to convert to angle, right, degrees, I could do times 180 divided by pi, which would be 75.2 degrees. Solving for this means this is 75.2 degrees. So APB is roughly 75.2 degrees. Okay, so that's part A. Part B. What's the height of the taller building here? Well, if you want to find what theta is, okay, so we get to use this one, but here. 75.2 degrees is given by 180 degrees, right? So that's the entire angle along the line, but we subtract 2 theta. So theta is going to be 180 minus 75.2 degrees all over 2. So theta is going to be somewhere around 52.39 degrees. So if you want to find h, we got to set up the right equation here. So we have the hypotenuse of this triangle and the opposite side length. Right, so our reference angle is theta. Hypotenuse is 150. Opposite side is h. So opposite and hypotenuse, how are they related? By sine. Right? So sine theta is opposite over hypotenuse. So h over, right? So h over 150 is going to equal sine theta right here. So height is 150 times sine of 52.39 degrees. Right, what does that give us? Well, in our calculators, that should be around 119 meters, rounding to 3 sig figs. Okay, so we're done with part 2. Let's move on to part 3. We have an equation that models the amount of drug in a patient's body. So this negative sign indicates decay. So I guess we would start off from some point and we're decaying all the way down to 0, right? Because as time goes to an infinitely large number, e to the power of minus kt would mean 1 over e to the power of kt, but this is becoming really large, which heads to 0. Right? So we know that this is a decay problem, and let's move on to what the questions are asking. So the amount of drug when t equals 0 is basically substituting in t equals 0. So 500 times e to the power of minus k times 0. What is the value of k? We don't know that yet. Do we care? No, because k times 0 is just 0. So 500 times e to the power of 0 is just going to be 500. Right? So that's a clean number. We start off with 500 milligrams, and we're expecting this to decay over time. Okay, so that's part A. After 3 hours, when t equals 3, the amount of drug in the patient's body has decreased to 280. Okay, so let's just check if we can use t equals 3, because other times we might have to convert this to either minutes or seconds, right? But it says t is a time in hours, so thankfully we can just write A3. So A3 is going to be 500 times e to the power of minus k times 3. This is said to be 280. So we solve for k. Right, so what we do, we would do 500, 280 over here. That's e to the power of minus 3k. Now, if you look at your logs and exponents formula, e to the power of x is y. If you have that, we can say ln y, natural log y, is x. So that means minus 3k can go over here. Then we can take this one over here as ln 280 over 500. Right, so k is going to be negative 1 over 3 times ln 280 over 500. An alternative approach might be to draw a line like that. Whoops. So if we say this is 280, and we say that this is going to be 3. Right? Okay, so actually this wouldn't work right now because you don't know what k is. So I guess this is the most cleanest way to get this done with. So let's go over to our calculators, see what this is. Okay, so we would get 1 over negative 3. Right. And then we multiply the natural log of 280 over 500. So if you convert that to decimals, that should give you somewhere around 0.193. Okay? So k is going to be 0.193. And once we have this k value, we can then fully graph this one. And later on, we can know any time value for which we have a known amount of drug in the system. Okay, so the second dose is given t hours after the initial dose when the amount of drug is 140. Okay, so we can use our value of k, right? So we have 500 e to the power of minus kt. So minus 0.193 times time. That's going to be our function of amount of drug, time. Start with 500, we're decaying like that. So we have our threshold point. When A is going to be 140, we want to know that's the time we administer the second drug, right? So t hours after that. Oh, it's 140, so we basically solve for when is our amount going to equal 140. So just like we did last time, we could just simplify this and solve for t. So we reserve using the calculator at the very end. So ln 14 over 50 instead of 140 over 500 is equal to t negative 1 over 0.193. So you could solve for this right away, or you could plot these two graphs and find the intersect, right? So let's look at both methods. So 1 would involve doing -1 divided by 0.193, and I want to use more precise numbers because rounding midway may lead us to lose information. Right? So if you do that, times ln of 14 over 50, right? So ln of 14 divided by 50, that should give us 6.59 hours, right? So, and we're going to get the same approach when we use a graphing method. So I'm going to plot my original graph, which was 500 times e to the power of minus 0.193, and I was 272 times x, right? So pardon me for not using t, we're going to use x. So that's one function right here. Oh no, we don't see it. Well, worry not, we're going to adjust the windows, right? So since we start off with 500 milligrams at t equals 0, obviously the y has to be much bigger than what we have here. So I'm going to give us some ample space. I'm going to start at like 700. And we're clearly not going to go below 0, but I just want to see the graph with some leg room at the bottom. So I'm going to write minus 100 as our y. Is it okay to write t as negative? Not really. Like, we start from t equals 0, but I'm just going to write from -3. Earlier, we kind of checked that the t is going to be like 6 point something. So we know that we're in the reasonable range, but I'm just going to see like t equals 30. I just want to see what happens 30 hours after after the patient takes the drug, right? So this is what the graph looks like. We start at 500 milligrams, and we're kind of decaying over time, right? So let's also add another graph. Right? So I'm going to add another graph here. We want to look at when this reaches the level of 140. Right? So finding the intersect at this point would give us when exactly the dosage remaining becomes 140. So intersect between these two graphs, between these 2 points. So when t is 6.59, the amount of dosage becomes 140. So capital T is exactly what we're looking for. So this is going to be 6.59 hours. So we used both methods, graphical and manipulating exponents and logs. Either way, this is what we get. Okay, let's now move on to number 4. We have the weight of a bunch of rice, right? So we have like bags that are produced in a factory. So there's bag number 1, bag number 2, bag number 3. We're going to have so many bags coming out every day, right? And imagine this happening for months and years on time. We're going to have so many bags, but we're going to record the weights of each of these bags, right? And they're modeled by a normal distribution with mean 204, standard deviation 5. Okay, so what that means is some bags might be 203 grams. Other bags might be 207 grams. And then we might have like 190 grams. We might have an extremely heavy bag of like 220 grams. It's going to be all over the place. But if you keep recording it, and if you kind of keep track of them over time, we might kind of have like our weight on the x-axis, and we might kind of count where each bag stands. So every time a bag is somewhere around 204 grams, you would just keep on piling it here. Right? So if you show like these relative frequencies, it all adds up to this normal distribution curve. It's a bell-shaped curve, unimodal. There's like one hill. It's like a one-hump camel, and it's symmetric. Okay, so if we were to find all these bags and take the average of the entire population of rice, right, rice bags, the average is going to be centered at 204. Some bags will be greater than that. Some bags will be lighter than that, but we see the diminishing frequency here, right? And we know that the sigma, standard deviation, is going to be 5 grams. So a neat way to write this is W is normally distributed, right? It's a normal distribution. In order to describe any normal distribution, we just need to know 2 things, the mean and the sigma, right? Mean and the standard deviation. So it's 204 is the mean, and 5 squared is a standard deviation squared. So technically this is a variance, right? So we just need to know what mean and sigma squared are. Okay, so anyways, this is our distribution. What's the probability that it weighs more than 210 grams, right? It's pretty neat. We just need to use normal CDF to find, okay, so for a normal distribution of mean 204 and sigma 5, I want to know the lower boundary being 210, the upper boundary being infinity. Like, I want to know the area under this curve. Right? So I want to know the area under this curve. that's greater than 210. Okay, so that's the first normal CDF we're going to use. And then in the second problem, we say that 80% of the bags are between W grams and 210 grams. Okay. Okay, so we'll first have to do part A. Then we're going to have some lower bound at part B here. Right? So this is going to be W. And we know for a fact that this area in between is going to be 80%. Right? So you just know that this is going to be 0.8. But let's first find out what this area is going to be. Okay, so we're going to head over to the normal distribution. So if we head over to our calculator, we get stats, normal distribution, right? And we want to do normal cumulative distribution frequency. So I want my lower bound to be 210. I want my upper bound to be infinity. So you could look for the symbol infinity, or it's perfectly fine to just say 1 times 10 raised to the power of 99. It's an arbitrarily large number. Mu is going to be 204. Sigma is going to be 5. So if you find that, that's said to be 0.115. Okay, so what that means is this area is going to be 0.115. So A, 0.115, that's that. W then, right, would mean it's at an area such that the combined area here is 0.915. So this area here is going to be 0.085. Okay, so I want to find the value of W. And I want to find the probability that it's less than W grams. Okay, so first, probability that our weight, capital W, is less than W, right? Okay, so the notation might be confusing, but if you say this is this concrete number here, right? This is W. W was the original weight of the bags. So this is going to equal 1 minus, we have the area 0.115, and then we have the area 0.8. So that's going to be 0.085. Okay? So the probability that our bag is under this weight is 0.085. And since we want to answer it in 3 sig figs, I guess we can't cut any corners. We would have to write 0.11. This one was 5069 from normal CDF. So we would have to write the full 0.0849. Right? If you wrote 2 sig figs, you're at risk of losing some points there. Then we want to find what W is. Okay, so the situation we have is this. We clearly have a normal distribution where the mean is 204, the sigma is 5. We have this W where the area from the leftmost part to this boundary is 0.084. What is W? Well, this is a case where it calls for inverse norm to be used. Right? So we're going to tell it the area from the left of this point is 0.0849. Mu is 204, sigma is 5. Okay, so let's head over to our calculator to see what that is. So I'm going to go to normal distribution from stats, and I'm going to go to distributions, inverse norm. My area is 0.0849, my mean is 204, my standard deviation is 5, right? That's what I get. Then I'm told this is going to be 197.136. So W is 197.136, which is roughly 197 grams. Okay? Part D. 10 bags of rice are selected at random. Find the probability that exactly one of the bags weighs less than W. Okay, so let me just write this here. So this is exactly the binomial distribution case we're looking for, because we're basically flipping a coin, right? We're flipping a coin, and instead of getting heads or tails, there's 2 outcomes. One is that the weight is greater than 197 grams. And the other case is when the weight is less than 197 grams, right? So this has a probability of 0.08. Okay, so we have 0.0849 as being lighter than W, and greater than W is 0.085. So we have to do 1 minus this, so 0.915, right? So these are the two probabilities, right? We either get a heads or a tails, like heavy or light. Now we do this 10 times. We're checking 10 bags. And we want to look for the case where one of them is less than this weight. So we want one bag to have this probability. The other bags, 0.915 probabilities, but we have 9 bags here. Are we done here? No, because if we say we have 10 bags right here, so we have 10 bags here, we could have this being a light one, and the rest could be a heavy bag. But that's not the only possibility. It could be the case that the second bag is a light one, and the rest are heavy. Right? So there's actually 10 different ways to choose a one light bag. So we have to multiply 10. Right? The more sophisticated approach would be to choose 10, choose 1 here. So if the question was asking like 2 of these should be lighter, then we would just adjust these numbers and write 10, choose 2. Right? But for now, we're just going to write 10. So 10 times 0.0849 times 0.915 to the power of 9. That's going to give us somewhere around 0.382. Okay. You could use your calculator for Binomial PDF, actually. So with Binomial PDF, what we're going to do is we're going to have 10 trials. The success probability of a outcome is 0.0849. We're going to observe exactly 1 instance of success there. Okay, so let's just do that. In our calculators, we're going to get probability or distributions, Binomial PDF. I'm going to have 10 trials. I'm going to have probability of success, 0.0849. I'm going to have just 1 success. That's 0.382, exactly in line with what we have right here. Okay. So we had a normal distribution. This time we know what the mean and standard deviation are. Then if you want to know like the area under the curve, you use norm CDF. Right? So norm CDF is a big thing that we're using constantly throughout. It's almost in every exam paper every year. Then we might use inverse norm. This is a case where we're using area to find the unknown value. Right? This is, we find the lower and upper bound of x, and we find the area under the curve. Right? So norm CDF is when we have the values on the normal distribution and we want to find the area between certain regions. Inverse norm takes the area, returns a point where we have like x. So for x, if we have a known area, what is this value of x? Right? That's what we're saying. And then there's a lot of cases where these normal distribution problems are linked with binomial distribution or binomial probability, binomial expansion, etc. But they don't explicitly use the word binomial. So how do you know when to use like binomial PDF or CDF? Well, basically look out for cases where there's 2 possible outcomes and n different trials. And we're observing like x successes or failures, right, out of n trials, right? Whenever you see these kinds of wordings or these kinds of scenarios happening, it's definitely a binomial problem. Okay, now let's move on to number 5. Okay, so the expansion of x plus h to the power of 8 can be written as this thing right here. Okay, so we're going to get x to the power of 8 first, because what we're doing here is imagine you're multiplying x plus h like 8 different times. Then in order to expand everything out, we got to take one term from each of the 8 here. So you could do like multiply out all the x's and get a x to the power of 8. Right. Next, we could get 7 x's and 1 h. Right. So we could choose x out of the 7 here, and then one of them is going to be a h. So we're going to get x to the power of 7 and then h. But there's 8 different ways to choose this, because there's like 8 terms here. And we need to choose 1 term out of 8 for which h is chosen instead of x. Right? Earlier, it wasn't 1, it was 0, right? We chose 0 terms out of 8 for which h is chosen. This time we have 1. So x to the power of 7h has 8, choose 1. Next, we have x6h2. So we choose the same thing, but we're 2 terms out of 8. Right, so for 2 out of 8 terms, we choose h over x. Right? So that's why we would have 8 choose 2 here. And we would keep on writing this. So that gives us a, b, c, and d. Okay, so if you were to write out these expressions, a would be 8h. Right? B would be 8 choose 2, then h squared. If you do c and d, okay, I guess it doesn't want to know what c is. We would get 8 3 h cubed x to the power 5 plus 8 choose 4, h to the 4, x to the power 4. Okay, so d would be 8 choose 4, h to the power 4. If you were to expand this, we would do like NCR, by the way. In your formula booklets, it should be given as n factorial over n minus r factorial, r factorial. So 8 factorial over 2 factorial, 6 factorial times h squared, which is 8, 7, 6, 5, 4, 3, 2, 1. 2 times 1 times 6, 5, 4, 3, 2, 1. So thankfully, all of these terms cancel out. We get 56 over 2, which is 28. So we would get 28 h squared. Similarly, 8 choose 4 is going to be 8 factorial over 4 factorial, 4 factorial, right? Because r is 4, n is 8, so n minus 4, or 8 minus 4 is just 4. Right? So you would just write 8, 6, 5, 8, 7, 6, 5, 4, 3, 2, 1. Then we get 4, 3, 2, 1, 4, 3, 2, 1. We just expanded all the factorials where we're multiplying from this term all the way down to 1. So all of these terms will cancel out. The 1 cancels out as well. We could take out the 8 here, then we could do 2 here. So we're left with 7, 2, 5, which is 70. So we get 70 h to the power of 4. That's our expression for D. You could go to the calculator for this. So a choose 2, a choose 4. The calculator can basically go to probability combinations. Right? 8 choose 4, that's 70. Go to probability counting combinations. If you have 6 choose, if you have 7 or 8 choose 2, right? 8 comma 2, that gives you 28. Right? So whether you use a calculator or whether you do this by hand, it's essential that you understand how binomial expansion works, right? So if this is unclear, you can go back to review that part. B. Given that a, b, d are the first terms of a geometric sequence, find the value of h. Okay, so 8h, comma, 28h squared, comma, 70h4. Okay, so if this is a geometric sequence, I'm going from one term to the next by multiplying a common ratio r. That means 70h to the power 4 over 28h squared, that's going to be a r, which is also equal to 28h squared over 8h. So this simplifies to 14 over 4, or 7 over 2 times h. This simplifies to h squared, 35 over 14, or 5 over 2. So if you want to solve for these, right? Like, here's a wrong way to go about this. If you just do 5 over 2h is 7 over 2, because you can just divide by h. And if you just go with h is 14 over 10 and h is 1.4, right? That's correct, but you kind of missed out on one solution. Because there's a case where, like, so the thing here is we divided out the h, so we just lost information here, right? The alternate way is to actually put everything on one side. Then we factor it out like this. So we don't cancel out the h, because h could be 0, or 5 over 2h minus 7 over 2 is going to be 0. So h would then be 1.4 in this case as well. So it's h is 0 or 1.4 instead of just 1.4, right? So here we lost out on info because we divided out the h. So technically, we wouldn't be able to divide away the h if it is 0. So it excludes the case where h is 0, right? But then again, this might not matter, because if you're looking for the geometric sequence, then h would have to be 1.4 and 1.4 only, since this doesn't make sense, right? The geometric sequence requires that r cannot be 0. Otherwise, you're going to have u1. u2 is going to be u1 times 0. u1 times 0 squared for the next terms, right? So we're going to have u1, 0, 0. So we can exclude h equals 0 naturally. Anyways, h is 1.4. That's how you do number 5. Okay, so this kind of combines the knowledge on geometric sequences and binomial expansion. Okay, let's now move on to number 6. We have a graph with velocity here, and this is a velocity per time, and we want to look for the case when acceleration is 0. Okay, so first, acceleration is found by velocity prime, right? Similarly, velocity is the displacement prime. If you want to find the total distance traveled or the total displacement traveled, we would have to integrate vt with respect to time from one point in time to another. And we might want to add the absolute value sign if it's for distance. Right, so this is something that you should be mindful of. So total displacement, which we might use later, would just be vt dt from time t1 to t2. If you were asked distance, it would be the same thing as displacement, but we would have to have a absolute value sign, right? So I'll go over this later. So A, find the value of t1. So t1 is when a t1 is 0, or when v prime t1 is 0. Okay, when does that happen? When basically we take the prime of this and set it to 0, right? So we could do this by hand, where v prime t would be, we use a product rule. So 4 times e to the power of t over 3 minus prime times cosine of t over 2 minus power over 4 as is, plus 4et over 3 as is, and then we get cosine of t over 2 minus power over 4 prime. Right? That's using the product rule to find the differentiation here. But since it's only worth 2 points, I would just go over to the calculator to find a graph for v prime t and try to look for when this becomes 0. Okay? So that's part A. Part B is the second time when the particle is at rest. So that's basically this point. This is the first point. This is the second point where the particle is at rest. So it might help to graph this out. C is going to be the distance traveled between T1 and T2. Okay, so as I said earlier, this part is positive distance because we have the particle moving in one way, let's say to the right. Then after coming to rest momentarily, this is a turning point where it's moving to the left. So this is negative distance. So if you have some particle going to the right and then to the left, right, adding this in full, right, this plus this is the distance. The displacement would be subtracting, right? Like this would indicate the displacement. Right, so if you just use integrate Vt from T1 to T2, we would be having positive area and negative area summed up, so that will kind of cancel out this part. But if you want distance, we want to keep the absolute value sign so that we can kind of account for all distances traveled, right? So if you move to the right and then come back, we're counting all movements, right? So that's what distance is. So again, we're going to use a calculator to have Vt from T1 to T2. Okay, so T1 should have been the, I guess that's the first time when the particle's acceleration is 0, so I'm guessing it's going to be somewhere around here. It's our first local maximum, local minimum point. So this is going to be T1. Right, so we're going to basically integrate from T1 to T2. Okay, so let's now do all this on our calculators. Right? So we got T1, T2, absolute value dt. Right? And then the second part would have just been when is Vt equal to 0. Okay, so let's see how we could do that on our calculator. So we're going to plot our calculator graph. So our expression for V is going to be e, so 4 times e to the power of negative 3x, or negative x over 3, negative t over 3, like that, times cosine of t over 2 minus pi over 4. Okay, so that's x over 2. And then, just to avoid confusion, I'm going to put a bracket around my x. Minus pi over 4. Right? So sometimes the calculator might confuse the order of operations. So you might want to keep everything nice and packaged in each brackets. So we're taking x over 2 first, pi over 4 next, and then we're subtracting the 2, and then we're putting that inside the cosine, right? So notice how many brackets there are, right? Like one bracket that you miss out or add in, that's going to cause a syntax error. So try to be mindful of that. Also, I want to make sure that my units are in radians, because unless the problem says deal with degrees, it's always radians. That's like the default. And we know that our graph is from 0 to 4 pi, right? Because time goes from 0 to 4 pi. So I'm just going to preemptively select my window settings to 0 to 4 pi, right? So 4 pi is roughly like 12.56. It's like 3.14 times 4. So I'm just going to write it maybe up till 13. You could choose to get a rough estimate of what y will be. Or another useful setting is zoom fit. So what zoom fit does is, given your x range, it's going to automatically adjust your y range for you. And for some reason, we don't see our graph right here. Okay, so let's see what happened. So I believe we entered in our function. Okay, so I think we kind of lost our info there. So for e negative x over 3 times cosine of x over 2, close brackets, minus pi over 4. Okay. Yep, and there you go. This is our VT graph. So first point, we want to look for when acceleration is 0, basically when we have a local maximum, or when we have v prime t is 0, right? So I'm going to go with analyze this graph. I want to find the maximum between this point here. Okay, so when time is 0.395, the velocity is 2.92. This is when the acceleration is 0. Okay. Next, I want to look for the x-intercept. So graph, analyze graph, find the 0 between here and here, right? Or actually, it's actually the case where the second rest is, so analyze graph, 0, here and here. So we know that at exactly, or roughly exactly at 11 seconds, the velocity is going to be 0, so it's going to be at momentarily rest, right? Next, I want to find the area between 0.395 to 11, but I also want to make sure that I'm adding, right? So I'm going to do integral. So if I do maybe, so if I go to integral, or I could do like bounded area from, I think you could type out analyze graph, bounded area. Okay, so the bounded area would work for two functions. So I would have to write in like y equals 0 there. But I could just do analyze graph, integral, and I would tap my function and I would basically drag my graph here. But I just want to make sure that I'm at 0. It's kind of hard to see what's going on. But okay, so let me just clear out everything. Okay, so what you can do is you can kind of create the integral for the lower bound being here, and the upper bound is going to be around here. So that's area 6.61. So this is all roughly speaking. Then the second set, I'm going to do area from 4.71 to somewhere around 11. So that's like 1.29. So I'm going to do 6.6 plus 1.29 here. Okay. Or if this is a bit confusing, what you could try doing is we could just write our expression that we need, and we could just do it manually. So what we had here was, so first of all, we had T2 is 11.0 seconds. T1 was 0.395 seconds in our graph. Then we do 0.395. And we do this until 11, and we do absolute value of 4 times e minus t over 3 times cosine of t over 2 minus pi over 4. So I'm sure on the actual calculator things are a bit smoother, but on this app there seems to be some issues with dragging. So I'm just going to write this here and solve for it. So if you do that, we should get something along the lines of 6.538 plus 1.293. So that adds up to 7.83 meters as distance. So that's how you do it. Otherwise, since we saw that this part was 4.71, you could also like break this integral down, right? So you could have 0.395 to 4.71 and VT as is, and then we subtract 4.71 all the way to 11.0. Right, so since this area is negative, subtracting this negative area will add everything up for you. But I would prefer to just use this expression right away. So let's move on to the calculator to calculate that expression. So as I said earlier, we're going to be integrating from 0.395 until 11.0. And we want to take the absolute value of our expression for v. So v was 4 times e to the power of negative x over 3. So that's x over 3 right there. And then we want to multiply times, we would get cosine of x over 2. Then we do minus pi over 4. Then we get x. So that should be 7.83, which is what we exactly expected. So performing this, we get 7.83. Right. Moving on to section B, we have number 7. So these are the more long response questions. So we need to have a continuous understanding of everything, because we might use info that's found in the earlier steps to solve the later ones, right? So let's try to keep the flow going, right? So I recommend like trying to go through this in one go, like instead of trying to flip through these pages during the exam, right? So in one sitting, we would do from part A, what's inverse h? Well, since x, or h, is kind of like y equals root 4x minus 2, inverse would mean we were to switch the x and y, right? So x would equal square root of 4y minus 2. Then we try to manipulate this such that we isolate the y here. So we could square both sides. So x squared is 4y minus 2. Then y would be x squared plus 2 all over 4. Right? So that's what we get for h inverse. But the thing here is we got to check where the domains are all working out. Right? So if you have this part right here, right? So it's basically when x is 1/2, y would just be 0. And we would get a graph that looks like that. Right? Taking the inverse would mean we're flipping this over y equals x. So we would start from when x equals 0, y would be 1/2, and we would go something like that. Right? That's h inverse, that's h. So this is the expression right here. Right? So we can kind of check that since x was greater than or equal to 1/2, y would have to be greater than or equal to 1/2. Right? Also, our domain would then be x has to be greater than or equal to 0. Right? So we kind of have the flipped switch here. Right? The domain was greater than or equal to 1/2 for h. A range was greater than or equal to 0. In the inverse, the domain and range are switched. Right? So just to recap, domain is the possible values of x that can go into a function. The range is the possible values of y that are output by the function. Okay? So that's that. That's A for you. And then let's look at graph of h and h inverse. Okay. So although I kind of drew my graph like that, maybe in reality, if you actually graph it, maybe the two graphs are going to intersect. Okay? So let's actually have a more clear-cut graph here. So let's say we're going to draw y equals root four x minus 2. So the calculator will do everything for you. So you don't have to be able to like necessarily sketch all of this, but it kind of helps to know that when x is 1/2, we're going to get y equals 0. And we know that we're going to get something like root 4 x minus 1/2. So compared to the graph of root x, right, like root 4 of x minus 1/2 is something that's horizontally compressed by a factor of 4. Right, so we're going to get like a very high, basically a very like skinny and tall graph here. So I guess when we have y equals x, we're going to have it trespassing, right, this boundary here. Right, but do note that when we have a function and its inverse, they will intersect at y equals x, right? Because h of x is going to be x, then h of inverse x is going to be y. Okay, so what I mean is y is h of x, then h of inverse of y is going to be x. But if you have a point on y equals x, that's just saying like x equals hx, so h inverse x is just going to be x. Right, so whenever we have a function and its inverse, they're always going to intersect on the y equals x line. Right? So you could do this manually, but you could just do this by hand as well. Right? So let's do this. I mean, you could do this by calculator, but you could do it by hand as well. But let's move on to our calculator, since in the exams, it's highly advised that you just graph this. Right, so if you go to the graph part, we would do square root 4x minus 2. That's graph number 1. Then we could add in another graph. Graph entry, function, and we had x squared plus 2 all over 4, right? So x squared plus 2 all over 4. And I think you should keep brackets here. Right? So we're not dividing the 4 just to the x, just to the 2, we're dividing the entire x squared plus 2 over 4. Right? So this is a graph we get. We can find the intersection with analyze graph here. So we want to find the intersection between these two graphs where the lower bound is here and here. So we get 0.586586. And we can find the second intersection between these two parts, so 3.41. So when x is 3.41 or 0.586, we get our intersection. Okay. Next, let's look at the area enclosed by these two graphs and then find h prime. And then when do these graphs have the same gradient? Okay, so first, the area enclosed can be done using this right here. So the analyze graph, the bounded area between two graphs. So if you look at the explanation here, tap two functions, then the bound. So we have the two functions, right? And we basically want to say, we want to find the bound between 0.586 and 3.41. Right? So if you find that, the area is going to be 1.89. So this automatically selects the two graphs for you. You just need to select from where to where we're finding this. So the area bound is just going to be 1.89. You don't need to show any work because it's all implied. Like if you found this, the examiners will know you probably use your calculator, but you could just do for your own sake of record keeping, like we're finding the area between 0.586 and 3.41 for the area where we have h of inverse minus h, because h inverse is at the top, h is at the bottom, right? And you could write out this expression as x squared plus 2 over 4 minus root 4x minus 2. Right? So either way, the area should turn out to be 1.89. If you want to do h prime x, right? So I guess you can't really use a calculator here. You got to use the full expression. Then we can use the chain rule. Right? So we have h is 4x minus 2 raised to the power of 1/2. H prime x is then, we bring out the 1/2 in front. Then we do 1/2 minus 1, which is minus 1 over 2. Right? So that's a power rule, because x to the power of n is going to be n times x to the power of n minus 1. Now, we don't just have x raised to the power of 1/2. We have 4x minus 2 raised to the power of 1/2. So we've got to multiply 4x minus 2 differentiated. So h prime x is then going to be, this is going to be a 4, by the way. So 2, right? So 4 times 1/2, so that's 2 times 4x minus 2 raised to the power of 1/2. So h prime x is going to be 2 over root 4x minus 2. That is what you get for h prime. Okay, so that was part D, finding h prime. And if you were to do part E, when will h and h inverse have the same gradient? So we want to look for when h prime x equals h inverse of x, like prime. There. So h prime x was 2 over root 4x minus 2, right, as you found earlier. If you want to do the inverse of that, right, since h inverse was x squared plus 4 over 2, 2 over 4, then h inverse prime is going to be 2x over 4, which is x over 2. So when will these two be equal to one another? Well, we could just solve for this using our calculator. That should give you, that should give you somewhere around x equals 1.77. Okay, so just to check, we could do, so we could just graph one function. So instead of 2 over root 4x minus 2 and x over 2, we could just draw one graph. Right? We could draw 2 divided by square root of 4x minus 2, close brackets. Then, if you were to subtract a x over 2, all we gotta do is set this to 0. That would mean the two values are equal. So when does this equal 0? The 0 is between 1.77, right? So the 0 of this graph, right? So when this pink graph is equal to 0, that means these two terms are equal to one another. So that happens when x is 1.77. Okay. Next, let's move on to number 8. We have a weight suspended on a spring, right? So in physics, we would draw a free body diagram, recognize that the weight is constant, but tension is constantly varying according to Hooke's law, right? Depending on how much extended or compressed length we have, the upwards force is constantly varying, right? So at some times the tension is small, weight is big. At some times the tension is far greater compared to the weight, so it's accelerating up and down, right? But anyways, this is like the, I guess, like background info that might help to know it, but you don't need to know this. We just know that the height is sinusoidal. So if you were to model t and h, we would see some kind of graph, right? That's going like that, up and down. We track the height. It's drawing a sinusoidal curve following a cosine function. Okay, so let's just analyze the movement for now. I guess later on we might have to deal with differentiation, but let's just focus on what the question is asking. So the period of the function. So if you have sine of at or cosine of bt, right? What we know is sine t and cosine t have a period of 2 pi. These are basically the function that has been horizontally dilated or horizontally stretched by 1 over a and 1 over b respectively, right? So this is a horizontal stretch. So if you want to find the period of any function in this form, the period is going to be 2 pi over b, right? In this case, 2 pi over a. So if you want to find the period of this function, period is 2 pi over 7.8, which is going to turn out as roughly 0.806. Okay. So a, we're done. We just divide 2 pi by whatever the factor of horizontal stretch or compression we have. All right, now let's move on to the next set of questions from B. So the height of the weight is at a minimum of 1 and at a maximum of 1.8, it seems. Okay, so it's going from 1.8 to 1. And this is a graph of h. And since our h of t has some unknown values, so it's a times cosine 7.8t. Right? So a times cosine 7.8t plus b. We want to fill in these, right? So let's actually compare this to the normal, like cosine 7.8t. If we just had a normal cosine graph, we know that it's going to pass from the maximum to the minimum, right? So for every period, which is around 0.806 seconds, what's happening is that we fluctuate between 1 and -1, right? We fluctuate between 1 and -1. The principal axis would be y equals 0. But for our case, the amplitude is 1.8 minus 1 over 2, which is 0.4. The principal axis, or the midpoint equilibrium position, however you want to call it, is 1.8 plus 1 over 2, which is 1.4. So with 1.4 as a baseline, the center, we're going up by 0.4, we're going down by 0.4, right? So in that case, we know that this graph has to be vertically stretched by a factor of 1 over 4, right? Or by 0.4. So stretching by a factor of 0.4, that's just like compressing. And we shift the entire graph up by 1.4. Okay? Also, the normal cosine graph starts from the max, then goes to the min, then back to the max, right? Here we start from the min, then we go to the max, then we go to the min. So it's a flipped graph. So I would say A would have to be negative 0.4, and B would be 1.4. Right? So we're using our knowledge of how a normal, like standard cosine graph looks like, and then we used our knowledge of function transformations, right, to see what A and B would be. One could argue that we could have like a normal cosine function and then shift it slightly so that we get our minimum and maximum switched, but that's not an option, right? If you want to switch, if you want to horizontally translate this, we would have had to have like t and minus c here, but since there's no horizontal shift, no horizontal translation, we know we have to resort to reflection, right? Like vertical reflections and stretches and vertical transformations, right? Translations to achieve our function here. Okay, next. What's the number of times for which the weight reaches a maximum height in the first 5 seconds? Okay, so if we just divide up the 5 seconds here, we'll have to see where it is. So it's like somewhere around here, but don't be too trusting of these diagrams. At times, these might not be to scale. So we know for a fact that t is 0.806 seconds. So we can work out 5 seconds over 0.806 to find out how many full waves we would fit in. So that's going to be around 6.2-ish. So we know that 6 waves definitely fit in for sure. Right? So if you have, say, so let me just use a marker here. So this one is 1 wave. Then we have another wave here. Then we have the 3rd wave, then the 4th wave, then the 5th wave, then the 6th full wave here. And then we have around 0.2 of a wave, right? So note that this would involve another 0.4 seconds from here. Or basically, this would be like the 6.5 periods. So if you went from 0 to 6.5 periods, that would be like the 1, 2, 3, 4, 5, 6, 7th peak. But 5 seconds only corresponds to 6.2 periods. So we're ending our boundary at 5 seconds, which is somewhere around here. So we're not going to include this one. We just have 6 peaks. So the question was asking not for the actual values of these times, but the number of times when the weight reaches a maximum. So we know that there's 6 maximums reached. Right, so it reaches a maximum height 6 times during the first 5 seconds. Now, when does this base of the weight reach 1.5 meters? Right? So when do we reach 1.5 meters? Many times throughout, but when does it happen for the first time? Well, we got to look at this one right here. So let's just set the equation ht equals 1.5, and we'll look for the smallest value of t for which that works. So negative 0.4 times cosine of 7.8t plus 1.4. That should equal 1.5. So let's solve for this. So you get 0.1 equals negative 0.4 cosine of 7.8t. Then cosine of 7.8t is going to be negative 0.1 over 0.4, which is just negative 0.25. So cosine of 7.8t is that. So 7.8t is cosine inverse of negative 0.25. Then I'm going to get t is 1 over 7.8 times cosine inverse of negative 0.25. You can either do that, or you could plot out the original equation right here as y is negative 0.4 cosine 7.8 t plus 1.4. You could also graph this as y equals 1.5, and you could find the appropriate intersections. Okay, so let's do that on the calculator. So if you do 1 over 7.8 times cosine inverse of negative 0.25, you should get 0.234 seconds, make sure that your units are in radians, right? So we're not dealing with degrees, so by default, we're dealing with radians. And let's also go to the graph to plot out negative 0.4 times cosine times 7.8x, close brackets, plus 1.4. Then let's also add another graph where we have 1.5, right? So y equals 1.5. So we're looking for the first intersection point. So analyze graph, intersection here and here. So when time is 0.234 seconds, we know that our base of the weight reaches 1.5 meters in height, right? So that's part D. So our answer is 0.234 seconds. So that's our answer for part D. Next, find the probability that the height of the base is greater than 1.5 meters during the first 5 seconds. Okay, so what we're looking for is, we know it's fluctuating throughout all these times. So during the first 5 seconds, we just need to find the entire duration for which this is greater than 1.5 meters. Okay, so we would go back to the graph here, and we will try to take note of all the times for which we are above the 1.5 meter mark. So what we have here is we're basically looking for the times during which this happens. So let's also find the other intersections. Right, so we have 0.234 seconds and 0.572 seconds. Right, so that's when we're above the times here. And we're also looking for the other intersections. Right? Here and here. So we have 1.04 seconds. So compared to the original, we're basically adding the period there. Right, so from 0.234, we are going to we're basically adding 0.806, which is what we get for 1.04. Right? And then we would find one more intersect from here to here. So 1.38, right? So that keeps on going. So let's try to wrap that around. So the first time is 0.234 seconds. The second time where it crosses paths is 0.571 or 0.572 seconds. Right? So we have one period during which we're above the 1.5 meter mark, right? So during this period of time, that's going to be roughly 0.338 seconds, right? So during this amount of time, we're above 1.5 meters. Now, how many times does that happen? Well, we do that for at least, let's see. So that happens for once, twice, thrice, 4, 5, 6. So that happens for 6 more times. And then there's a bit more that we're looking for. Right? But it says during the 5 seconds. Okay, so we would get 0.338 times 5. Right? And then we can say that during the first 5 seconds. So we get 1, 2, 3, 4, 5, 6. And then we have to look for the next case. But the thing is, we basically have the 5-second mark prematurely ending with the 6th peak. So we just need to multiply this for 6 more times. Okay, so what I mean by that is, if you take a look at this entire graph here, right? Let's actually draw when x equals 5, right? So if you were to add a graph here, So if you were to add a cutoff point, so let's say if you were to do value, or if you were to do actions calculate and 2. Okay, so if you look at a graph entry, and let's add a relation where x is going to equal 5. Right? So if you see the cutoff point, we know that there's 1, 2, 3, 4, 5, 6. There's exactly 6 periods during which the weight is above the 1.5 meter mark. So what that means is we have 6 of these cases. So that's going to mean we're going to have 0.338 times 6 seconds. That's the entire duration during which our weight is above this mark over the entire 5-second duration. So that's going to give us roughly 406 as our probability. So the probability that the weight is greater than 1.5 meters, that's going to be 0.406. Okay. Finally, let's move on to the last problem of our paper. So we have a probability case. So we have a bag that contains n balls. 10 of them are green, the rest are red. Okay, so if you have a bag of n balls here, we have 10 green ones, and n minus 10 would be red. So we're drawing the balls from the bag without replacement. Okay, so the first ball drawn is green. I guess that would just be 10 over n, right? Because n would be the total possibilities of the balls that can be drawn. 10 of them are our target event, right? The first 2 balls are green. That would basically be 10 over n, right? Then the next decision actually depends on the outcome of the earlier one, right? So since we drew 1 ball, we now have n minus 1 remaining. And there's also 9 green balls remaining. So we got to multiply these two. We would get 90 over n squared minus n as our probability. Right? Next, let's say n is 25. The probability that the first 2 balls are red is 0.35. Okay, so let's think about complementary events. We would basically have the first 2 green balls, right? So instead of going for like green, we could go for red, then red, right? So we could do n minus 10 over n, or we could do 1 minus 10 over n, right? Or actually, since we're given the value of n, we don't need to deal with this. We'll just do like, in the first case, we have 25 balls, out of which 10 are green and 15 are red. So 15 are red, 10 are green. In the next bag, we have 24 remaining. Now, if you're doing that, we found the red one on the first one. Right? We draw a red. Then we have 14 red balls remaining and 10 green balls remaining. So the probability of all this, we multiply 15 out of 25 times 14 out of 24. So if you simplify all of this, we should get 3 over 5 times 7 over 12, which is 14 over 60, or 7 over 30. So 7 over 30. Okay, so 14 over 20. So that's 3 over 5. So that's 60 and 21. Right? So 21 over 60, which is 7 over 20, which is roughly 0.35. So we pretend like we didn't see this number. We just solve as is, right? What's the probability of drawing a red on the first one and drawing a red on the second one, right? If you multiply these two events, the probabilities, we get 7 over 20, which is 0.35. Right? So that's how you do part B. Next, probability that the first 3 balls are red. Okay, so this case is also just using sequential events. So the first, we have 15 out of 25 balls. Then we have 14 red balls remaining out of 24. Then we have 13 red balls remaining out of 23. Right? So you just calculate all that. On your calculators, we should see 0.198 to 36 figs. And find the probability that at least one of the first 3 balls is green. Okay, so this is a complementary case because the opposite of the first 3 red balls being red is at least one of them has to be green, right? So 1 minus 0.198 means not all 3 are red. That's the equivalent statement of saying at least one is green, right? So we get 0.802. We don't need to spend too much time on calculating this, right? So the probability of drawing red 3 times in a row is 0.198. Then we would have drawn at least one green, right? Whether it's drawing one of the green balls or 2 green balls or all 3 green balls, right? Anything that's not in that 0.198 is our desired probability. Right? Next, a game is played where 4 balls are drawn, one after the other, from the bag of 5 balls. Okay, so there's a lot of rules to shift through, but let's try to break this down. Okay, so the first one is that we start from 25 and we're basically going through 4 draws. Right, so in the last case, we'll have 22 balls, out of which 1 will be drawn. The player earns points based on when the first green ball is drawn, and then at the end of each game, so after this is done, we're putting it all back. Okay, so there's a complicated rule saying there's 0 points if no green ball is picked, or if the first green ball is picked on the first or second draw. Okay, so the player earns 10 points if the first green ball is picked on the third draw, and earns 50 if the first green ball is picked on the fourth draw. Okay, so let's actually find the case where she's drawing the first green ball, right? So it's all a matter of when does she draw her first green ball, right? So let's just say X, right, is the event where she draws the first green ball on the Xth draw, right? So let's say X could be 1, 2, 3, or 4, where we're picking the first green ball on the first, second, third, fourth draw. X equals 0, let's just say that she picks all red balls. Right? So all 4 of the draws are red, right? Because, so basically if you have the table of points here, if X equals 0, 1, 2, 3, and 4, if she picks no ball, or if she picks the first green ball on the first or second draw, right, that's basically her getting 0 points. So X would be the event, then we'd have the points. Then we might want to leave a calculator section, section for calculating the probability of that happening. Right, next up, the probability of her earning the first green ball on the third draw, right, that's a 10-pointer, or a 50-pointer if she picks it on the fourth draw. Okay. So what's the probability of each of these happening? Well, we would have to calculate that based on, so I don't want to use the word negative binomial, but it's basically, we'd have to calculate all the products. Okay? And then we're going to do k times. Okay, so we would have to find the expected probability. Okay. Okay, so let's first find the expected score. Then the expected score times k must be greater than 100. Right? So we're going to find the respective probabilities and then find the k that we need so that she can earn at least 100 points. So I'm kind of running out of space, but let's try that. Okay, so let's say we have X equals 0. Then it's basically her drawing red like all the times, right? And then we'd have her drawing red on the first one, and then the green one, and the second one. Okay, so to sum it up, like the expected score, right, That's basically going to be 0 times the probability that x is 1, x is 0, right? Because that's the points you earn versus the event happening. 0 times probability of x being 1, 0 times probability of x being 2, and then we have 10 points for the probability of x being 3, meaning the probability of you earning a green ball for the first time on the third draw. Then we have 50 times probability of x equals 4. Okay, so actually, we don't necessarily have to calculate this, right? So let's just cross that out. Let's just find what's the probability of these two events. So we earn a red ball on the first draw, a red ball on the second draw, and then we want to earn a green ball on the third draw. What comes next doesn't matter, right? Because we could draw either a red one or a green one, doesn't matter. So this entire thing multiplied by 10, plus we draw a red ball on the first draw, red ball on the second draw, red ball on the third draw, and then we choose one of the green balls when there's 22 left. The rest doesn't matter, because whether we are choosing red or green on the next subsequent draws, it doesn't matter. She already stopped playing the game, right? So this gives her 50 points. So if you were to calculate this on your calculator, right? So if you were to put this expression on your TI calculator, we would get somewhere along the lines of 6.0178 or somewhere around 6.02 points. So her playing the game, she's expected to win 6.02 points. So 6.02 times k is going to be 100. How many times does she have to play? Roughly 16.6 times. Right? But she wants to earn more than 100 points. So she has to play more than 16.6 times, or she has to play at least 17 times. So the least value of k games she has to play is 17. Right? If she plays 17 games, her expected score is going to exceed 100. Any less than that, it's going to be less, right? Less than 100. So she must play at least 17 times. Okay, so the last problem was a bit tricky, but let me just highlight the key concept you needed, right? We had the probability, we had the formula for expected value. So we do x times probability of x equals x. So this is like the sum product. We have the probability of x happening. So we have the value of x. In our case, that was like the points scored on a game. And we multiply that to the probability of x. Right? So basically the probability of winning that many points. So since 3 out of 5 outcomes, right? So we had 5 possible events, drawing the green on the never, or the first draw, second draw, third draw, fifth draw, right? So there's 5 possible events, but 3 of them were worth 0 points. So this kind of excludes the necessity of having to find those probabilities. Then we had x equals 4, x equals 10, right? And x equals 50, right? So the probability of finding a ball on the third draw, right? That gave you 10 points. Probability of finding a ball on the fourth draw, that gave you 50 points. So we did 10 times that probability, right? And 50 times the other probability, right? So 10 times drawing on the third plus 50 times drawing on the fourth, right? So that was what we went through to find the expected score of 6.02. That led us to say, okay, you got to play at least 17 times if you want to score 100 or higher. So that was what we did for this question. That wraps it up for number 9, as well as this entire paper. So that was 23, May, paper 2, Timezone 2.